So where we actually start off this unit, I'm gonna dive into unit number one here, so we can take a look. We essentially had 4 weeks of work just to kind of summate this entire thing. In week one, I mean, that was really touch and go, just some basics on there. We're looking at, okay, can you actually touch anything or not? And just trying to get to know you guys a little bit as I can through the screen. In our overview, you can see real quickly, hey, how small is an atom? Just getting some mind to think a little bit about this. So for our purposes of testing, not so important. On the other hand, though, when we got to week two, we started to actually dive into this. So within week two, we're sitting here looking at a bunch of information. So we've got scientific notation and we've got the metric system and also some conversions. So in our overview of week two, it's pretty important that we are able to basically talk this idea of, well, how do we actually do scientific notation, metric conversions, and make sure we can go back and forth between this. For your actual summation or your test in this case, there's very little on here, and most of it can be tied back to this video from week two, where you could just revisit and take another look at it, or you could take another look at your formatives from this week because they're still open, so you could still plug those back in as you kind of go through. Week three, however, was where we actually started to pull out some of the history related to the atom. And that's where this got kind of confusing because I was trying to sum up almost 5,000 years of chemistry into sort of one spot. And there's this really long video and this whole thing about, okay, well, what do we do with this specifically? Well, there's some general takeaways we should have concerning kind of the history of the atom. The first one I really wanted to look at was the cathode ray tube. And in this case, this was J.J. Thomson, but I don't care so much that you know what the cathode ray tube is doing, just the idea that there's this beam. So when the beam is actually applied to an electric field, like a positive and negative, the beam goes straight down to a positive. Now that's really important for us because that basically tells us that beam has negative pieces. So essentially what we find out is that there's an electron inside of the atom, and it's got those negative pieces. And so we look at it, and Thomson develops the plum pudding model, which is kind of this, what you're looking at here, this positive charge or goo is spread out, and we got these electrons sort of sitting on the outside. And this is the model that's sort of what we look at. Now, why did he come up with this? Well, he knew there was negatives. The cathode ray showed us that there were some negative pieces in it. And so then he thought, well, let's make a model. And the focus is, we know there's negatives. How do we put the negatives in the model? Spread the negatives out. Well, they got to be attracted to something. So spread out some positive goo that holds the negatives in place. And that makes sense. I mean, we have negative charge. The charge is figured out by looking at the electric field. Okay. And then we make the model that has the negatives inside of it. So then Rutherford expands upon this and he says, here's what should happen if I shoot positive particles through. So positive particles, these alpha particles, should just fly straight through the plum pudding. If plum pudding is correct, then these things are going too fast. They're going to just go straight through into the other side. So now here's what Rutherford saw. I mean, he's not seeing those atoms, but he can actually see where these particles are traveling. Is that these particles aren't going in perfectly straight lines. Some of them are actually deflecting off the side, and every once in a while they bounce. And so he says, well, it can't be plum pudding because these are positives, and positives don't like other positives. The only thing that's going to cause another positive to move is a positive. Now that's weird. So the only thing that's going to cause a positive to move is another positive. So that means if those positives are moving, they're running into a positive. And so if we're looking at the plum pudding model, that doesn't make any sense because the plum pudding model would basically say that all the positives are spread out. So they have to recreate the entire model. But the focus here again is, how does he know this? He knows that the alpha particle is positive. He knows that positives don't like other positives. So if alpha particles move, it's because they're running into positives. So he develops the positive charge to basically be the nucleus, or this entirety of where all the positivity is on there. Now, this isn't quite accurate because it's showing some neutrons in there yet. He didn't know this just yet. But the positive alpha particles, if they get too close, won't touch. They'll bounce off. And so that's what he's really looking at. And so finally, we look at the neutron. And this is actually really confusing how they figured out there was a neutron in there. The basic idea, and I stole this from someone else, obviously, is they're kind of running through this. They're like, oh, here's a 1910s model. We got this proton sitting on the inside, electron on the outside, blah, 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 blah. And then we're like, okay, cool, check this out. 2 hydrogens should weigh as much as 1 helium because helium is the second element. And then when you put it on a balance, you're like, wait, it doesn't. 2 hydrogens is less than 1 helium. That doesn't make sense. And they're like, well, this helium is heavier than we thought. And so then they draw in, okay, well, what if, how many hydrogens would it actually be? Because we know hydrogen is just a proton. It's actually four. So four hydrogens is equal to one helium. That doesn't make sense. How can four protons be equal to two? There's got to be something else inside of it, something else inside that's showing us to give us that mass. And so that's the idea of the neutron, how it first came to be, but that's not actually what the evidence was. So the evidence, as we kind of went through this, and he's still talking about this idea of where these extra masses are coming from. Scientists knew that there's something else inside the nucleus. They know there's some particle in there. They don't know what it is. And so Chadwick sets this up. He shoots alpha particles through beryllium, boron, or lithium. And what he finds out is that this radiation shoots off. Now, what's weird is this is essentially a particle being shot off. And so the question is, well, what is that particle? It's not an alpha particle because the alpha particle is sticking to this and then shooting something else off. So once these elements get hit with the alpha particle, something else goes off. Now, what's interesting about this is that this something is no charge. It's a particle that has no charge. So if you were to interact it with an electric field, it wouldn't move. Okay? And what's even weirder about this is when he goes ahead and puts some wax on the other side of it to get hit by this. Sorry, I'm kind of jumping through here a little bit. And they put some paraffin or essentially just candle wax on the other side of where this is happening. Protons shoot out. And not only that, they shoot out really fast. And the only way a proton could shoot out really fast is if something the size of a proton was hitting them. Now, we already know that whatever this is doesn't have a charge. Now we just figured out that whatever this thing is going to be the same size of a proton. And so that he uses this example at the bottom. If it was something that was really small, like a BB, and it hit a pool ball, you wouldn't see the protons shoot out that far. So whatever's hitting the protons has to be about the exact same size as the protons. So imagining basically a pool ball hitting another pool ball. Only this pool ball has no charge. And this essentially is how the neutron was discovered. So if we're looking at mass, we look at this idea of things we already know that have mass and are heavy, versus things that we know that, like an electron that doesn't really have mass. We're looking at charge, we're trying to figure out, okay, which way are things deflecting? We know that this has no deflection, so this must be neutral. We also know it's about the size of a proton because it's causing the protons to bounce out into another form. And then we go to the Bohr model and we look at specifically, okay, how does this whole thing relate to light? So the only thing you have to really understand about this is that we're way out in that fourth ring and you want to jump down. The only way to get back down toward the nucleus to jump to the first one is to release energy. Now you'll notice I released purple light. Well, purple light is really high energy. The further you jump, the more energetic the light's going to come off. Down to orbit 3. Now I just emitted some red light, which was actually off the chart. You couldn't even see it. Orbit 3 to orbit 2. There's some red light. So 3 and 2 are actually closer together. This model isn't perfect, but the closer together they are, the less energy it takes to release. So if we were to look at an atom where the further away these orbitals get, the closer they are, little jumps release small energy light or reds. Big jumps release high energy lights or purples. And so the entire spectrum of light, if it's more purpley, like on that edge of the rainbow, that's high energy. If it's more reddish, that's the low energy stuff. So if we're seeing a spectrum like this, you'll notice that this one released a low energy one and then two high energy ones. If we had a green in there, it'd be like a middle energy one. So you can imagine 3 jumping to 1 maybe as a green. We can try that and see what happens. So we'll bounce out to 3, jump to 1, still purple. What you'll find out is that a lot of these things as we jump pretty much make purple or red, and the greens are even more confusing to see. So for our purposes, all we have to understand is the bigger the jump, the more energetic the light. The smaller the jump, the less energetic the light. And high energy light is purple, blues. Low energy light is reds, oranges, and then yellow and greens kind of in the middle. And then once we got to actually building an atom, and we knew that there's protons and there's neutrons and there's electrons inside of an atom, we started being able to count them and sort of take a look at what the atom would be. So we realized that charge is just going to be the balance of protons and electrons because those are the positives and negatives. The neutrons and protons would be our mass because the electrons essentially don't have any mass. And so we went to symbol form, and the symbols helped us to identify a lot about these particles. So in this particular case, we've got hydrogen. It's got a mass of 2. It's one proton, that's the atomic number, and it has no charge. Now, normal hydrogen that we tend to see in the environment is not this hydrogen 2, it's actually hydrogen 1, meaning it actually doesn't have a proton, or a neutron, sorry. And the electrons aren't really doing orbits, they're like doing this. And it's like, okay, let's just focus on an orbit. So if a hydrogen loses its electron, what's kind of weird about it is it's just a proton flying around. And sometimes, actually in biology class, we'll talk about hydrogens floating around as just being protons, like a proton pump. It can pump hydrogens across the cell one way or the other. And then if we go to like other elements and we start adding some more protons on here, well, the number of protons is going to affect what element you have. The number of neutrons will start affecting the mass you have. And so we can have like things like lithium 6. And then if we want to balance the charges, we need the charges to be balanced out with the electrons. And all of this was kind of taking us to this idea of how do we count those subatomic particles? Because in reality, here's where we wanted to go. So what we wanted to do is start looking at actual isotopes. And an isotope, it really just means the same atom, but a different mass. So if it's the same atom with a different mass, you could think hydrogen 1 or hydrogen 2. Now, both of those are hydrogen. Now, one is a mass of 1 and one is a mass of 2. And you may have noticed in your periodic table that the masses are decimals. And that's kind of strange because how could it have part of a neutron? And the answer is it can't. Instead, if we look at symbol, we can also look at abundance in nature. So for example, hydrogen 1, 99.9885% of all the hydrogen is hydrogen 1. But hydrogen 2 does exist. And so if you were to look at the mass of your periodic table, you'd see hydrogen's mass on average is 1.01. It's almost 1. But that those hydrogen 2s make it, there's a slight amount. To give you sort of a visualization of this, here's what this would look like in a sample. All the purples on here are hydrogen 1s. And then the green is the one hydrogen 2 sitting there, which gives us our average mass of 1.01. So if I were to pick a different element like boron, and we just looked at boron and you looked up the average mass, you'd see it's 10.8. And I could tell you, well, 80% of the boron is 11 and 20% of the boron is 10. So it's pretty close to an average of 11. Now, 10.8 is not perfect. Carbon's got a mass of 12.01. So you'd expect most of the carbon to be carbon 12, and it is. There's very little bit carbon 13. Actually, there's even less carbon 14. And you can see this as you kind of play around with the elements, that the various mixtures of them, oxygen's got 3 flavors to it, but almost all of the oxygen is oxygen 16. And so all of those masses you're seeing on your periodic table are average masses, which basically tell you the different kinds of isotopes you have, whether it be 16, 17, or 18, but also their abundance. If the average is almost exactly spot on, that's how much you really have sitting inside that system. Okay, so what do we actually have to know? For the most part, there can be broken down into just to a couple stages. Metric units, metric conversion, and scientific notation just takes practice. There's not much to it other than just the practice. Don't forget, kids hate deans because deans call mommy is an easy way for us to remember which way we're moving the decimal place. Big important pieces that we have to understand about the historic relevance of the atom is that mass determination is done by basically calculations, but also interactions with other pieces of matter. Charge interaction is done by interactions with other kinds of charges. For example, in the cathode ray tube, the electron was determined to be negative because it attracted to a positive electric field plate. A proton was found to be very massive because it was taking up the entirety of the nucleus and, when bombarded with alpha particles, could force them out of each other's way. Neutrons were also very massive because they could dislodge protons in Chadwick's experiments. The idea here is that the data observations lead to the actual models. Bohr's model, the idea of how much energy is being released as the electrons fall down, basically tells us that the larger the jump, the more energetic the light. In other words, if an electron falls from many levels down to another lower one, a large energy type of light, mainly ultraviolet or violet, it will be released from the atom. If it does not jump as far, you would expect something like the infrared or red kind of a light to fall. Counting subatomic particles for us is basically just keeping in mind that mass is always going to be the number of protons plus neutrons, and charge will always be the protons minus the electrons because the electrons are the negative value. Keeping that in mind, we can look at the actual isotopes, or same atoms but different masses, and figure out that the average mass written on our periodic table is just a representation of the abundances found in nature. Therefore, if it is determined that over 99% of the sample is of one isotope, you would expect the average to be very, very close to that isotope number. For example, with hydrogen 1 having 99.9% of the sample being hydrogen 1, the average mass is 1.00794, or about 1.01.